Leonardo CAMELI, third-year PhD student from the University of Bologna, and I'm working on the road department. Today I wanted to present you the methodology for assessing the quality of cycle routes in kinematic and behavioral terms used for the Florence case study. In this presentation, I will show you the first result related to this methodology. The aim of the research is to define a methodology to evaluate the cycle infrastructure from different points of view: the safety and road perception, the maintenance of the cycle infrastructure, the speed and performance of the cyclist in different bike sections. For these purposes, our department has equipped this bicycle with different advanced sensors: the Garmin, which includes a positioning system and internal memory to store data from other Garmin sensors that are including in the bicycle, a speed sensor and a cadence sensor. In addition, we have an inertial measurement unit, IMU, and a profilometer to measure the distance from the rear seat to the ground. Together with the instrumental bicycle, the participants of the test wear a device for assessing the mental workload and stress. The Mindtooth is an advanced psychophysiological monitoring technology based on the use of the sensor to measure brain activity and other physiological responses. It is composed by an electroencephalographic EEG sensor to detect electrical activity in the brain. These sensors are placed on the scalp and collect signals representing brain activity. After that, the data collected is transmitted to a device that processes it in real time. Mindtooth software analyzes EEG signals using advanced artificial intelligence and machine learning algorithms. The analysis makes it possible to extract useful information regarding the physiological state, such as attention level, stress, and other cognitive and emotional conditions. In addition, the participants wear a topic glasses 3, that is an eye tracking device capable of continuously detecting the driver's gaze while cycling. The eye tracking system is integrated into glasses so it's easy to wear and it has a minimalist design. Data are monitored via software application and recorded on SD card. The signal sampling is up to 50 Hz. Based on these devices, our research group built an experiment focused on the perception of the distant cycle path by the user with respect to the kinematic cognitive parameters. The workflow, as we can see in this chart, is composed by several steps. The first one is the data acquisition from the different sensors. The step 2 is related to the data and sensor processing for the analysis of the eye tracking and the EEG analysis. After that, we move to the step 3, the data analysis, that include the user speed, pavement, and human factor analysis. In the step 4 will be an aggregation and classification of the final results using statistical analysis as well. Moving to the case study, our research group tested in Florence in the middle of June a cycle route in an urban context. The aim of this experiment was to understand how is the perception of the state of art and will be correlated with the redevelopment of the area due to the introduction of a neutral line next year. The cycle route was divided in 5 sections from A to B with different typology and length. The sensor has defined also the arithmetic profile of the case study due to a barometer altimeter sensor. The participant so has to ride from A to B and back. The architecture of the test includes a sample of 18 participants with heterogeneous characteristics. The test was carried out in 2 days between 9 p.m. and 9 a.m. and 3 p.m. The participants to travel the cycle path defined by their own trip, and it needs 10 minutes to make all the route, and the sample is composed mainly of male between 30 and 40 years, and the use of the bicycle by the participant is rare, but who takes often the bikes ride more than 5 kilometers. The first results is regarding the speed and the cadence, that was the rotation per minute. The Garmin Edge device made it possible to record the kinematic parameters of the bicycle in the different analysis sections using the GPS. From the GPS position, cadence and speed were calculated both for each analysis. The section 3 and 4, as we can see in the slide, show the lowest speed, and the section 2 the highest one. The reference value that represents non-degraded pavement is 835 millimeters. So from the profilometer is useful for measuring of the distance from 0 to 30 centimeters between the top of the rear seat and the road surface. The measuring rate is 1 to 500 Hertz, with sample rate is 30 Hertz. A range of distance will be defined to understand which is the pavement with more obstacles or holes. For the moment, we calculate the profile from the rear seat, and we set the value that we measure from a pavement in good condition. The next analysis focused on the vertical acceleration. The low ISO 2631 gives the acceptable values of vibration magnitude for comfort that we call RMS. Is it possible to apply also to the vibration of the bicycle? According to it, the analysis cycle route show a very good comfort, around the 60% of the total route. What about the tracking analysis? Analyzing the most critical section 3 and 4 in terms of speed and vertical acceleration, it was possible to find that users on average tend to look straight and are very little attracted to the surrounding road environment. In section 4, near passing traffic vehicles catches an average of 20% of the total picture, an indication that they perceive this section most dangerous than the other one. At the end, we analyzed the three main outputs from the mind device. For the stress, the higher value is for section 3, workload section 4, and the worst value for the vigilance is for section 4. So it is possible to conclude that section 4, from the cognitive point of view, has associated the most workload and the least value of vigilance, due probably to the temporary condition of the bicycle path and the great proximity to the vehicle flow. We can define the stress, a psychological response to the situation. The workload is the amount of the cognitive resources required to perform a task, and the vigilance is related to the attention and focus on specific tasks for long periods. So it's possible to conclude after this first analysis of the different devices that the section 2 records the higher speed and cadence. The user slowdowns are recorded in section 4 with a protective bike lane configuration, and the adjusted barrier is where to slow down the most. So the people perceive the section 4 like the most dangerous, so they brake a lot in this section. What about the pavement condition? The worst results are generally found in section 3, that is a mixed-use path made by blocks. For the vertical acceleration, as we say, the 60% of vibration in that direction are acceptable. Subsequent analysis, we investigate the section to identify areas where the pavement needs more maintenance. Moving to the user visual behavior, in the most critical section 3 and 4, the user tend to look straight and are not very attracted to the surrounding road environment. However, in section 4, the proximity to vehicular traffic captures about 20% of total fixation, indicated a perceived danger. And at the end, from the cognitive outputs, the section 3 has the highest stress value. Section 4 indeed is associated with the highest cognitive workload and the lowest level of vigilance, probably due to the temporary condition of this bike path and the close proximity to vehicle flow. So it's possible to conclude that the section 3 and 4 are the most perceived dangerous for the participant that did the test. Thank you for the attention.